Hey everyone, welcome to another video. We've talked quite a bit now about Pythagoras' theorem, but a lot of the examples we've been looking at, we have mainly tried to look at this Pythagoras theorem in 2D, so on a flat plane of space. We haven't yet looked at some of the really cool applications Pythagoras' theorem has when we look at something in the third dimension. So not just these plane shapes like the triangle, but also how we can use what we know about right-angled triangles and Pythagoras' theorem and we can use this to apply it to working with 3D shapes and finding out information about 3D shapes that we otherwise wouldn't be able to know about. So let's just jump into just a couple of examples in which we try to locate right angles in these types of 3D shapes. Now I've drawn a rectangular prism here. So I'm just going to draw these in just to make it look nice in 3D. And in this 3D rectangular prism, we can actually make a couple of right angle triangles. What if we, say, went from this corner up the top down to this corner in the bottom and over to here? If I drew a couple of things in here, you will hopefully see that I can actually make this right angle triangle inside my rectangular prism. Now, why is this a right angle triangle? Because I have a perpendicular height to my flat base. So that's always going to be a right angle. In this shape, we can also get a right angle, perhaps from, if we go up here, down to here, over to here. If I connect this, and I connect this up to there, it's kind of hard to visualize, but if we were to rotate this prism around, we would also see this second right angle triangle that we've made. So in a lot of these shapes, we can locate these types of right angle triangles. And you may remember when we looked at some of these Pythagoras' theorem problems and using especially real world examples, we were kind of making these fictional, we were kind of constructing these right angle triangles in the real world. But now here, when we have these types of shapes, take now a cylinder, for example. We can now locate in actual shapes we already know, we can locate some right angle triangles. What about a cylinder, for example? Well, if I draw from, let's say, the center of this bottom circle out to one of the edges, and up to the top of my, actually, let's go, because I got to sync this up to the middle, up to the top of my cylinder, and join up all of these, I once again see that I have a right angle triangle making up this shape in some way. Well, not really making up the shape, but just being located within this. Now, if I jump to another tab as well, I have an example on GeoGebra in which we just have a regular triangle, but we're going to trace this out and rotate this to see what type of shape it makes. So if I take this bottom bit, and I can see if I rotate this around, I'm making a type of shape that this right angle triangle is always present in. See if you can figure out what shape this is. Now this guy here is actually a cone. This is a 3D cone. if I draw this over here, draw my cone, I can see that my right angle triangle is always present in here. Whether I draw it like this, or if I rotate it to another position, maybe out to this edge and up, I get another right angle triangle. Or if I go from here out to this point and then up to here, I get another right angle triangle. Now this is kind of maybe hard to visualize, and it looks a little bit messy here. That's why I gave you guys that example before, but we can locate a bunch of these right angle triangles in a lot of our 3D shapes, and that's kind of what we're going to be doing in this video. So I've just drawn 4 in here. They look a little bit messy, but as I rotate my bottom around, I have a bunch of different right angle triangles I can construct inside my 3D shape, my 3D cone. Now, this is just to give you a bit of a visualization for how we can apply right angle trigonometry, Pythagoras Theorem questions and techniques that we've learned, how we can apply this to 3D shapes. And now we're going to do one question in which we're just going to try to find some kind of calculation and apply everything we've learned about being able to find these right angle triangles in our 3D shapes. We can construct them in a number of different ways. So let's jump into a question. We have here the length of the diagonal on the base of the rectangular prism is 8.3 meters. So that's this guy just down here. So the diagonal on the base of this prism is this line through here. And the rectangular prism's height is 3.9 meters, so up here. Find the distance from one corner of the rectangular prism to the opposite corner, and give your answer correct to 2 decimal places. So what they mean here is, well, one corner up the top, can we find the difference between that one and say this one down on the bottom left corner that I've already drawn? Well, from this diagram, if we break this up, we can actually see that if I were to, I have 2 out of 3 of the sides, but if I were to join from this bottom corner all the way up to my top corner, I can see that I can make a right angle triangle. I have my right angle down the bottom here, and all of these sides make up a right angle triangle. So if I take, and what's important here is that it's one thing to see these in there, but when we're actually doing calculations, it's a little bit tricky to apply Pythagoras' theorem because you're trying to visualize a 2D shape in 3D space. So what we want to do is we want to work with this triangle separately. So we're going to pull out the triangle. So pull out the triangle from my solid. From our solid. So I've identified the triangle. Now I just want to kind of cut and paste it outside. So what this is going to do is this is going to make the question far easier to deal with. See, I've taken this and the orientation and I've just pulled it out. So my right angle goes down here, my 3.9 meters goes up here, and my 8.3 meters goes down here. So this is my right angle triangle going from 3D space to 2D space. So it's going from a 3D prism into a 2D triangle on a sheet of paper. Now what this allows us to do now is I can find this length from one corner to the opposite corner by just solving my Pythagoras' theorem for this hypotenuse here. So I'm going to call that C. And now we are going to apply Pythagoras' theorem. So let's call this C meters. So Pythagoras' theorem tells us that this side C squared is going to be the sum of one side squared as well as the other side squared. So that's going to give me 8.3 squared plus 3.9 squared. And now this pronumeral, it doesn't have to be C. It can be D for distance. It doesn't really matter. I'm just using C because we use that when we dealt with right angle triangles and Pythagoras' theorem. Our C was always our hypotenuse. So I'm just doing this here like this. And now, to solve this, we want to just find what C is. Because we're not looking for C squared, we're looking for C. So in order to find C, I can just take the square root of both sides. Because taking the square root of both sides is going to undo the C squared to just give me C. And it's going to give me a length for it when I put this 8.3 squared plus 3.9 squared under my square root. So when I pop all of those into my calculator, I'm going to wind up with two decimal places, 9.17 meters. And we can either write this as we can write this to, for example, 2 decimal places, or we can write this as a surd. So we can write this as 9.17, or we can write this as the square root of 84.1, I think it is, to if we want a more accurate answer. But for this, the question asks us to leave it in 2 decimal places, so I'm just going to leave it as 9.17. And now, just quickly, because anytime we did Pythagoras' theorem and anything else in maths, we want to do a little bit of a sense check. Does our answer, 9.17, make sense? Well, for this 2D thing, it does make sense because our hypotenuse is always the longest side. And 9.17 is longer than 8.3 and it's longer than 3.9. And also in this picture, if I zoom in, it looks as though the diagonals, so from this red dot up here to this one down here, that looks like, just by looking at the shape, that it's going to produce a very large length, larger than even this side here, or this one up here. So our answer makes sense, so we have used Pythagoras' theorem correctly. But that is how we can apply Pythagoras' theorem to 3D shapes. We just want to locate the right angle triangle within our 3D shapes, either our prisms or our cylinders or cones, anything. And then we want to pull it out. We want to translate this from 3D into 2D because it's easier to work with. So we want to just convert this in a sense, and just drawing the triangle, pulling it out and writing it on our paper, so it becomes a really easy 2D Pythagoras' theorem question. And then we just apply the actual Pythagoras' theorem to find our answer. That's all for today. Thank you so much for joining me, and I'll see you in the next video.